Hello everyone, welcome to lecture number 5th of week 7. This is the last lecture of week 7. In this week we had seen Lagrange's mean value theorem, Cauchy mean value theorem, general case of the Cauchy mean value theorem as well as generalized mean value theorem, and some of the problems which are directly applicable for Lagrange's mean value theorem, Cauchy mean value theorem. So, this week is totally devoted for Cauchy mean value theorem and related problems. The last lecture I have chosen for problems as well as some of the assignments. Those problems, as you had already seen in the last lecture, where we had used the Lagrange mean value theorem and we had given some counter example when to Lagrange mean value theorem cannot be applicable for that problem, right? So, let me start this lecture with very basics one from the Darbox theorem, Rawls theorem, Cauchy mean value theorem and all those. Recalling Darbox theorem is a good idea to have the understanding of the differentiability or the slope of the tangent line at a point C between a closed interval, right. So, Darbox theorem says that if a function f is derivable on a closed interval AB and f dash b are of opposite signs. So, you have one function in a closed interval AB fx, and you have at end points you have f dash of a and f dash of b are of opposite signs. It is not at the same sign, but it is of opposite signs. So, when you have opposite signs f dash and fb, then there must exist some point C. As you can see, I mean, in a normal way, as you can see here, that if I have like this and if I want to have something like this, right. So, this is the point A and this is the point B, right. And let me erase first and then do some more problem for you. So, here and choose the ink like this. So, say here. So, if you have some of the function like this and we have here a and we have here b, say. So, here the slope line, as you can see here, the slope line is something like this, and that means the slope is positive here. But look at this point, and if you find out the slope of that point, this one, so this or something this, okay. So, erasing this one and let me do again some of something like this, right. So, I can find this. So, this point is, let us say, B, right. So, how much the slope of the opposition, this is the slope. So, this is less than 0 and this is greater than 0. So, these are the two opposite signs. So, there must exist some point C here, between the C here and which as f dash of C is equal to 0. So, maxima or minima may exist at that point, right. We had seen for extremum maxima or minima value theorem, right, in the Rawls theorem slides. What is the Rawls theorem? Rawls theorem says that if fx is a real valued function, is continuous in a closed interval AB and differentiable in an open interval AB, and fa and fb are equal, that what we are talking about like this. So, if we have here as A and here as B, so fa and fb are equal here, and the function is continuous as well as differentiable, then there exists at least one value of x on AB, call it C, such that f dash of C equal to 0, at least one value. See, there are many C, not only one, but there are many C between this. But the theorem say at least one C, that does not define the uniqueness of the C. So, there may be a different type of different various numbers of such C, such that f dash of C is equal to 0, right. If two points of the same height are connected by a continuous differentiable function, then there has at least one place between those 2 points where derivative or slope is going to be 0. Similarly, Lagrange mean value theorem, in the previous slides and lectures, we had explored the Lagrange mean value theorem, where we have f as a continuous function in a closed interval AB and differentiable function in an open interval AB. Then there exists some point C in open interval except at the end points open interval AB, such that we can calculate f dash of C as the ratio of the difference between the functional value and its argument, right? That is the Lagrange mean value theorem. And Cauchy mean value theorem, the same value, we have extended the Lagrange mean value theorem into the Cauchy mean value theorem by introducing another function gx. So you have fx and gx as a two function, and both are continuous in a closed interval AB and differentiable and open interval AB, and g dash of x is not equal to 0 throughout AB, then we can calculate f dash of C into g dash of C, the ratio between the ratio of the slope of the two lines f dash C and g dash C at the point C, such that it is nothing but it is equal to its functional value GB minus of GA. So, FA minus FB divided by GA minus GB. This is the Cauchy mean value theorem, and if you extend another introducing the another function Hx, then it will become say general mean value theorem. So, what will be the generalized mean value theorem? If you have f, g and h from where to where, from AB to R as a real valued function which is continuous in a closed interval AB but differentiable in open interval AB, and if we define dx as f of x, g of x, h of x, f of a, g of a, h of a, and f of b, g of b, h of b as a determinant, then d dash of C is equal to 0 for some point lying between A and B, right. So, that is the 5 theorem from the Darbox, Lagrange, Cauchy mean value theorem, generalized mean value theorem and Rolle's theorem. These 5 theorems are play a significant role in derivative and differential calculus. Now, we will use all this theorem as in the exercises as well as the problems. So, first example, look at the example first. I have chosen those examples to boost your concept that when you can use those theorem and when you are not able to apply these theorems, right. So, the first theorem says find the value of C for which satisfies the conclusion of the mean value theorem in the interval minus 2 to 3, fx is given, right. So, to apply the mean value theorem, the function must be continuous in that closed interval as well as must be differentiable in the open interval. Do you think that this function minus modulus of x minus 2 plus modulus of x in the interval minus 2 to 2 is differentiable? So, I mean, to do this, let us first draw the function. So, fx is modulus of x minus 2 plus modulus of x. So, x equal to 0. What will be the value of f of f of x? This is equal to minus 2. So, 2 and plus 0 is equal to 2. So, here for 0 it is 2, right. Now, for x equal to 1 or x equal to 2, what will be the value? You can see here x minus 2. So, 2 minus 2 equal to 0. So, 0 and 2. So, this is equal to 2. So, for x equal to 2, the value is the same as x equal to 2. Can I calculate x equal to 1? If you calculate this x equal to 1, it will be 1 minus 2 equal to minus 1 and modulus of that is 1 plus of 1 equal to 2. Can you calculate x equal to 1 by 2? So, let me calculate this x equal to 1 by 2. So, what is the value? This will give you 1 by 2 minus 2. So, this will be minus of 3 by 2 modulus plus of 1 by 2 modulus. So, this will comes out to be 2, right. So, that means from 0 to 2 the function value is 2. So, here is the function value. 2. And now use x equal to, so this value is 2, right? X value is 3. So what it will give you? This will give you 3 minus 2 equal to 1 plus of 3 equal to 5. So it will increase here or somewhere here and so on. That means this is your required value and this is your required value. Now the function is continuous in the whole interval minus 2 to 2, but it is not differentiable as the slope here are different. This is the corner line. So the slope from this line to this type is different, and henceforth the function is not differentiable. Once the function is not differentiable, we cannot use the mean value theorem, right? So straightforward, you can write down the mean value theorem cannot apply in this case due to the functional failed to be a differentiable function in that interval. Now look at a problem where Rawls theorem is applicable or not for the function f(x) equal to greatest integer model x, and the interval is given 5 to 9. So here 5 to 9 we can do this 5 to 9, from 5 to 9, right, 6, 7, 8, right? And I believe that you must remember about greatest integer of x. So greatest integer is not continuous at the point where at every integer, and henceforth from there to there the greatest integer is not going to be continuous at that point, continuous at the every integer 6, 7, 8 and 9, right? So at the integer point, at the integral point, at integral point 6, 7, 8, 9, 5, it is not continuous, and henceforth the Rawls theorem does not apply. Rawls theorem only apply when function is continuous. Now look at the third problem. Verify Lagrange mean value theorem for the function f(x) equal to log of x on 1e. That means this log x, that means you can use the ln and that will be much better actually. Log means the base is 10, but you have a natural logarithm as the base is e, exponential. So okay, let's do this. So for Lagrange mean value theorem, I have to check that this function is continuous in a given interval. So the given interval is 1e, 1 to 2e. E is what? E is an exponent function and it's it lying between 2 to 3. 2 to 3, it's approximately 2.713, right? So that means you have some idea E is an irrational number. It is an irrational number. You cannot write E as a p by q in the form of a p by q. So it's an irrational number, and you have the value between 2 and 3. So the function is continuous in a closed interval 1. Why? Because every logarithmic function is continuous in a closed interval which is greater than 0, and it is differentiable in open interval 1. Thus all condition of mean value theorem are satisfied. Now I have to find out the point C, right? So to find out the point C, firstly let us find out the value of the f(x) at those endpoints. So I will calculate f of 1, f of 1 is equal to log of 1, f of e is equal to log of e, and f of e minus f1 is equal to, we have to return f dash of c equal to f of e minus f of 1 divided by e minus 1. Therefore, f of e minus f of 1 can be calculated. F of e minus f of 1 is equal to f dash of c into e minus 1, and f dash of c is unknown right now because we do not know the c value. So this will give you log of e, this means logarithm, natural logarithm. So this will be 1 and log of 1 equal to 0. So this means 1 minus 0 is equal to f dash of c and divided by e minus 1. So take this e minus 1 this side, and this will give you f dash of c equal to 1 divided by e minus 1. That is one problem. But we can find out the f dash of c directly from the given function, because since the function is differentiable, I can have the derivative of that function in that closed interval. So, what will be the derivative of log x? Log x is 1 by x, right? So, f dash of c is equal to 1 by c. But we have calculated in the previous slides here, f dash of c is equal to 1 divided by e minus 1. So, I can equate this one, e minus 1, and then this will give you c equal to e minus 1. So, this will be your answer, where you will find the c, and now you can check whether the c lies between our given interval. So, the interval was 1 to e, and e I took approximately 2.713, and what will be the value of e minus 1? So, 2.713 minus 1 is roughly 0.71, 1.71, right? So, 1.7 is somewhere here, 1.71 is, that is e minus 1. So, that means this is the point, this is the critical points where the function has the derivative equal to the differences of the end points functional value by argument value. That means the Lagrange mean value theorem is valid for this problem. And what are the applications of the MVT? So, we have read all those Lagrange mean value theorem, Cauchy mean value theorem, generalized mean value theorem, and so on, Rawls theorem, Darboux theorem. What will be the most favorable applications? Some of the applications you will see directly, just like velocity. So, what is the velocity? Velocity is just the derivative of the positions vector, right? What is the acceleration? It is just the derivative of the velocity vector, and so on, right? But making this applications of the mean value theorem, you must need to understand that it is very much useful to find derivative of a given function when some of the points are unknown. So, either you are given a point, then you will find the derivative, or either the derivative is given or some number is given and you have to find the c such that f dash of c is equal to that point. That are those problems where you can find out. The second use is determine whether the function is increasing function or decreasing function. You will directly use the mean value theorem to get that idea. So, various applications of the mean value theorem are written here. For any two function f x and g x, if they are continuous in a closed interval a b and differentiable in an open interval, then we knew that if f dash of c equal to g dash of c in the whole interval a b, then f x minus g x is constant. See? So, you can easily find out that if there are two functions and if both their derivatives of the both functions are equal, then those functions, the difference of f x minus g x is going to be constant, right? It is used in physical interpretation like a speed analysis or acceleration or so on. If the derivative of the function f x is greater than 0, say here, it says that f dash of x is greater than 0, then f x is strictly an increasing function. This is a good thing. You do understand that if I find out the derivative of any function in a given open interval, then I knew that this function is going to be a strictly increasing. That means monotonicity will be valid for that function, and so on. If the derivative of the function f x is less than 0, then f x is strictly a decreasing function. On the similar line, and then Taylor series number theory use the mean value theorem very easily. So, what is the increasing function? I will give you some idea about the increasing function, and then there are some examples where we can see that either these functions, the given function, are increasing or not. The function y equal to f x is said to be an increasing function of x in the interval a b. Say here the interval is now, it is open interval because we are talking about some differentiability, that is why it is open interval. If the derivative of the f x is positive in the whole interval, f dash of x is greater than 0 for all f x equal to this. So, then it is an increasing function. Similarly, decreasing. So, test whether the following function is increasing or not. So fx is given, and I have to test in the whole real line. So calculate f dash of x. F dash of x is what? 3x square minus of 3x plus of 3, right? Make this 3x square minus 3x plus of 3, right? So make this one something like 3, why it is wrongly written, 3x square, and this will be 3. Okay, so this will be 6 of x, and this is 3, and that is right one. So now we can write down 3 into of x minus of 1 into 2. No. So take common of 3, so this will comes out 3x square minus of 2, and this will makes you plus of 3. So the whole thing will become x minus 1 into 2 is always positive when x is not equal to 1, x is greater than 1, right? So that's, so f dash of x is going to be 0, greater than 0 for all x belongs to R. So fx is an increasing function for all x. And okay, so let me give you some idea why it is written like this. So this is not the way to write this one. So 3 of x square minus of 2 and plus of 3. So this will comes out to be 3, this is common. So this will comes out to be x square minus 2 plus of 1, right? So this will give you, where is the x? X is here, x is the here. So 3 of x minus 1 ka whole square. So it's not 2 here. So it's wrongly written here. This is x minus 1 whole square, right? And a square of any number is always positive. That's why x minus 1 ka whole square is always positive, and henceforth the f dash of x, now f dash of x, 3 into some of positive number is always positive, and henceforth this function is an increasing function. Similarly, find the value of x for which the function this is an increasing function. Fx is given, find out f dash of x. F dash of x is coming out 3x plus 2x plus 6. Now make this function, since you want to be an increasing function, make this derivative as greater than 0. To making this derivative greater than 0, you will have the x plus 2 and x plus 6 is greater than 0, right? X plus 2 is greater than 0, x plus 6 is greater than 0, and this will give you x is greater than minus 2, x is greater than 6. So once you have minus 6 and minus 2 here, and it is greater than, so this will comes out to be minus 2 to infinity, this one. So in this region, if x lies, then the function is increasing. And again the second case will be both are negative. So x plus 2 is less than 0, x plus 6 is less than 0, x plus 6 is less than 0. So what will it come? It will come minus 6 to minus 2. So that's why taking this one, this interval from where to where, minus infinity to minus 6, the function is increasing function. So we have a two interval for which the function is increasing and decreasing, that is minus infinity to minus 6, and then we have minus 2 to infinity, right? Infinity, this one. So only except minus 6 to minus 2, the function is an increasing function. So that is a very beautiful applications of the mean value theorem, where you will find fx is an increasing function everywhere except minus 6 to minus 2. Similarly, decreasing function, do the in the similar line, that if derivative is less than 0, it will in the whole interval, then it will be a in a decreasing function. And here given the f dash equal to minus 10x square plus 40x, find the interval fx is increasing or decreasing, right? So f dash of x is given. So therefore, for increasing and decreasing, we have to put critical value. So f dash of x is less than 0 or greater than 0. F dash of x is greater than 0. So I am quite interested to find out this point actually. So this point is 4 and 0. So this point is 0 and 4. and as you can see, there are three intervals, minus infinity to 0, okay, now I'm going to change this color, minus infinity to 0, 0 to 4, and 4 to infinity. These are the three intervals. Now check each of the interval the behavior of the f dash of x, right? F dash of x. How we can check that one? So putting x equal to minus 1 here, f dash of 1 is equal to how much? Putting at x equal to minus 1, f dash of minus 1 is going to be minus 10 and plus of 40, minus 40, minus 40, right? So this will be minus 50, which is less than 0. So f dash of x is less than 0 in this interval. F dash of x is less than 0, herefore this function is decreasing function. This function is decreasing function where minus infinity to 0. Now check similarly you can check for x equal to 1, it will going to be positive. So f dash of this one, f dash of x is greater than 0. So this will fx is an increasing function. From where to where? From 0 to 4, and from 4 to this is less than 0. This is less than 0. F dash of x is less than 0 for 4 to infinity, therefore it is a decreasing function. So now it's a good thing to realize that any function may behave differently in a different closed intervals in a real lines. So you have the whole real line minus infinity to 0, 0 to 4, and 4 to infinity, and as you can see here, the function is decreasing from minus infinity to 0, then it becomes increasing function. This is an increasing function here, and then it will become again a decreasing function. Isn't it something like qualitative behavior changes with the interval itself? And for you, using the mean value theorem, these are the practice questions to you. Please go through it and try to find out the answers of all these. And I believe that this is the exhaustive, I mean we call it extensive lectures on the mean value theorem, and I believe that you do understand the mean value theorem in extensive way. So thank you so much.